Now I'll tell you another way to do the scaling process. This method is specially tailored to the conditions of boundary layers. It's very similar to the previous one, so I will save you the trouble of copying. I just wrote it out for you. You see here, x, the non-dimensional x, I define that to be x over L, and the L here is the length of the board, the boundary, right? And the y, non-dimensional y, is y over delta rather than y over L. Delta is the thickness, and y lies within the thickness because we are considering the boundary layer. So this thing should be a number between 0 and 1, right? Non-dimensional velocity u is u over capital U. This capital U is just the mainstream velocity, but the v, I'll define it by v divided by capital V, and capital V we define it to be the max vertical velocity in the boundary layer. P equals P over P naught. P naught is the max pressure, the max pressure value in the boundary layer. So you can see, since I defined the quantities in the denominator to be the max value, then all of these non-dimensional numbers will lie in the range of 0 to 1, which means they will all have an order of magnitude of 1. So if we plug these non-dimensional quantities into our equations, then this is the form we should get. Now here again we assume that delta is very smaller than L, and we can say that delta over L, we define that here, let's say, to be epsilon. Epsilon is a number that is smaller than 1, much smaller than 1, at least 1 order of magnitude, right? So delta over L is order epsilon. L over delta is epsilon to the minus 1. Epsilon minus 1. Epsilon minus 2, right? Here we have epsilon minus 2. Epsilon minus 1. Epsilon minus 1. You see, since we defined all variables, all non-dimensional variables, to be order of 1, then if we manipulate them, they will still have an order of 1. Say du dx. This thing will give me a term that has the order of 1, right? If this is the order of 1, then and this is the order of 1, right? We know if two things add up to be 0, then they must be of the same order of magnitude. So this term as a whole should give me a term that is of order 1. So what must u over u, v over u give me? It must give me a quantity of order epsilon, right? So v over u is epsilon. Only in this case will we get a term of order 1 for this. So v over u is epsilon. Here, epsilon. Here, v over u, epsilon. V squared over u squared, epsilon squared. V over u is epsilon. V over u is epsilon. Okay. So now let's look at this equation. Here, 1, right? Here, again, this thing, the manipulations of non-dimensional numbers in this case will just give me order of 1. So together, this term is a term of order of 1, right? So the left-hand side is order of 1. So must be the right-hand side, right? The right-hand side. So first, let's look at here. We see this term has an order of 1, right? But this term has an order of epsilon to the minus 2. What is epsilon to the minus 2? is a very big number, right? Epsilon is a very small number, so epsilon to the minus 2 is a very, very big number. So this thing is very, very small compared with this thing. And now we want this side to have an order of 1. So we need to compromise with this term or this term, right? We need to neutralize its order to be 1. And this thing, we know it will always be 2 orders of magnitude lower than this thing, which means this thing would be negligible later. So we must require this thing to be of order epsilon to the power of 2, right? Only in this case will we get this term as a term of order 1. So this is the, we know what this is, right? It's 1 over Reynolds. So this explains why we choose Reynolds to be order epsilon to the order of minus 2. We can analyze this in a mathematical sense. Also, note this effect. Oh, I forgot to tell you. In our equation, in our derivation, we assume the simple case that our fluid is steady. So I didn't write the du dt term. But the idea is the same, okay? I'm showing you this method of doing the scaling just to broaden your horizon, you can say. The result we get, the Prandtl boundary layer equations, it will be the same, okay? So here, we know this term basically represents the acceleration, or you can say the inertial forces, right? Here, what's this? What's this? It's the viscous forces. So we know the viscous forces and the inertial forces. They cannot balance each other at all times, right? So we need something to compensate for the difference of them, which is this pressure. We know they are of the same magnitude, so the pressure should also be of the same order of magnitude. So this thing will give me an order of 1. This is 1. So this thing, P naught over rho u squared, must give me an order of 1. Okay, we are basically at the end of the analysis. Here, 1 over Reynolds is just this thing. Here is 1. Here we have 1. 1. Well, again, same as the method we used before. We can neglect all the terms with a lower order of magnitude, right? Here, we can neglect. Here, it's 1. So this thing, all combined, will give me an order of epsilon to the minus 1. Well, all the others have an order of, say here, order of epsilon times 1 epsilon, right? Here, epsilon squared, epsilon minus 1 epsilon. All the other terms, this term, well, here is epsilon cubed, so this thing we can neglect. But here, epsilon to the minus 1 times epsilon, this thing gives me an order of epsilon. Well, this is an anomaly, right? Epsilon minus 1 is a very, very big number. So how can we deal with this? We must let this to be 0, right? Only in this case won't this term break our harmony, right? So only when dp dy equals to 0, which means later when we translate back to the dimensional equation, will give me dp dy equals to 0. Okay, so besides that, if we require this thing to be 0, then this we do not need to consider anymore, and the whole equation will very peacefully, a very small value equals to another very small value, so this equation we can basically neglect. and we are end up with the continuity equation and this equation where we can neglect this term, right? And transformed back into the equations with dimensions, we will get the same result, which is the Prandtl differential equations, Prandtl boundary layer differential equations.